Hello everyone, this is our heat conduction equation video discussion, and we are from group 9. The members of the group 9 are me, Harvin Singh, Noor Aini Najiha, and Lim Jazen. The question we got to answer for this video is a cylindrical fuel rod of thermal quantity of K equals to 30 watt meter Kelvin of 2 centimeter in diameter is encased in a concentric tube and cooled by water. The fuel rod generates heat uniformly at the rate of 100 megawatt per meter cube, and the average temperature of the cooling water is 75 degrees Celsius with the convection heat transfer coefficient of 2500 watt per meter cube Kelvin. The operation pressure of the cooling water is such that the surface temperature of the fuel rod must be kept below 200 degrees Celsius to avoid the cooling water from reaching the critical heat flux CHF. The critical heat flux is a thermal limit at which a boiling crisis can occur that causes overheating on the fuel rod surface and leads to damage. The first question is to determine the variation of temperature in the fuel rod temperature and the temperature of the fuel rod surface, and the second question is the surface of the fuel rod adequately cooled. Okay, the first thing that we have done is assumption. So the first assumption is the heat transfer rate is steady and only occur in one dimension with thermal symmetry about center line. Secondly, the thermal conductivity of the fuel rod is constant. And thirdly, the rod surface at R equals to R naught is subjected to convection. And finally, heat generation in the rod is uniform. Okay, next, the properties of the fuel rod is the thermal conductivity K equals to 30 watt per meter Kelvin. The heat generation in the fuel rod is 100 megawatt per meter cube, and the heat transfer coefficient is 2500 watt per meter cube Kelvin. The analysis that we have done is for one dimension heat transfer in the radial R direction, the differential equation for the heat conduction in cylindrical coordinate with the heat generation is expressed in the beginning of the calculation below.
So this is the equation for this problem, and then you need to integrate it twice. So first integration you get this one, and second integration you get this one, which is the general equation for this question, and then where C1 and C2 are the constant.
Okay, next, applying the boundary condition gives you R equals 0, the dt over dr equals 0, so this will give you C1 equals 0. Next, when the boundary condition is R equals to R naught, the equation Q equals to HTR minus DMM will get you the heat convection equation. However, from here you will get this one from the previous equation, which is this one. So we substitute this one into the equation by eliminating the C1 equals 0. And next, you will get this equation after combining the previous equation, which was this one, also from the previous equation, which is this one, eliminating the C1 here equals 0. So the final equation you get is C2 equals to E generation RO over 2H plus E generation RO squared over 4K plus T ambient. So this is the final equation of the C2.
Solving for C2, you can get this equation, but we need to substitute C1 and C2 into the general solution, and this is the general equation. So after substituting, we can get, this is the final equation to get the answer. Lastly, we need to solve the equation before. So first, we need to find the temperature at R equal to 0, which is at the center line of the rod. So T at R equal to 0 equal to 100 times 10 to the power of 6, which is given the heat generation, and 4 over K is given also, and R naught is 0.01, which is the radius given in the question, and you need to substitute all the value. H is equal to 2500, and T ambient is equal to 75 degrees Celsius is given in the question. So then we get T at R equal to 0 is 358 degrees Celsius. Next, the temperature at R naught equal to 0.01, which is at the surface of the rod. So this is the equation after we cancel from the general equation. So we get this value. H is given, R naught 0.01, and the ambient is 75 degrees Celsius, so we get the answer 275 degrees Celsius. So finally, we know that fuel rod surface are not cooled adequately.
Finally, the discussion. The fuel rod is not adequately cooled. This is because the temperature of the fuel rod surface is 75 degrees Celsius, higher than the temperature necessary to prevent the cooling water from reaching the CHF, which is below 200 degrees Celsius. Thus, to keep the temperature of the fuel rod surface below 200 degrees Celsius, the convection heat transfer coefficient of the cooling water should be kept above 4000 watt per meter cube Kelvin. To do this, we can either increase the mass flow rate of the cooling water or lower down the inlet temperature of the cooling water into the flowing into the side of the fuel rod. Okay, that's all. Thank you.